Bismillahirrahmanirrahim. We have seen in the previous classes that for a material to undergo brittle failure, that is failure without any warning, the crack length in it must be equal to AC, corresponding to the stress it is subjected to. For subcritical crack lengths less than AC, there shouldn't be any worry about the material breaking catastrophically, because the moment this crack achieves AC, the length AC, critical crack length, after that, uncontrolled crack extension is energetically favorable, so nobody can stop it. But before that, in case of subcritical cracks, the process of taking a crack from subcritical level to critical level, that is energetically unfavorable. So a crack that is smaller than the critical crack, it should never become as large as the critical crack length. So there shouldn't be anything to worry about. Now this is true as long as the loads we are talking about are static. On the other hand, if the loads are dynamic or variable, that is, their magnitude and direction changes. If a body is subjected to some sort of a fluctuating load like this, now here the direction is being changed. You can have something like this also, and then something again like this. If you're talking about such loads, then by virtue of something called fatigue, there's a possibility, in fact a probability, that over a period of time, it may take months, it may take years, in terms of revolutions of machines, maybe thousands or millions of revolutions, but someday a subcritical crack will increase to critical length. And when that happens, after that, there's catastrophic failure and nobody can stop it. So this phenomenon of fatigue, which you're going to hear a lot about from now on, it only happens when there are dynamic loads. The static loads have nothing to do with fatigue. Now, how does fatigue do it? First of all, what does fatigue do? Now, first question should be, well, it extends subcritical cracks to critical lengths. This is what it does. It doesn't need to do anything more than this, because once it takes the material here, then after that it doesn't need to do anything. You know what happens after that. Now, this is an important thing. There's an important distinction that needs to be made. This is the dividing line. The fatigue crack growth, the growth from here to here, this region, but the fatigue crack growth is slow, stable. By slow, I mean it could take thousands or millions of revolutions for it to achieve this goal of taking a subcritical crack to the critical size. Stable. If fatigue takes such crack length from 0 or somewhere around here to this point and then stops, whatever is happening, we stop the dynamic loading on the body, then the crack stops here. It doesn't extend one bit. So it's always, there's nothing uncontrollable about it. As compared to this, just compare what happens after this line. Catastrophic fracture. Brittle fracture is catastrophic fracture. It is fast as compared to this. It's a fast process. It's unstoppable. Once you are here, after this, nobody, you don't have time to stop it. It just runs away. Whatever you have to do it in this region so that the crack doesn't reach this threshold. These are two distinct things separated by this barrier here. Now, this next question should be, how does fatigue do it? Fatigue does it by utilizing stress concentrations. Now, this concept is familiar to you. We have seen it already many times. There's a crack here, so the stress trajectories have to perforce, they have to pass like this. So this is crowding here. So here there is a region of very high stresses, and this is called stress concentration, because crack or even the other faults, for example, sharp corners, holes, and what have you, they are all called stress raisers because they raise the stresses in the vicinity of their ends. So the stress concentration is there. Now, how does fatigue utilize stress concentrations? Obviously, we have already seen that it's a slow process. So what it does, it does its job one step at a time. One step at a time. It's in no hurry to damage the material. So how it does its job is something like this. What is going to follow is going to be a little simplistic, but it captures the situation nevertheless. Here a crack is there, and just assume that the crack is there already. We'll discuss how and why a crack should be there. Crack is here, and this is the point where there is a very high stress concentration, and the material is ductile material. We are only dealing with ductile materials, tough materials. So there are at 45 degrees you have slip planes, and there are a number of slip planes, complementary planes. Now at this point, when you apply the loading, you apply the tensile loading, what happens is that there is an atomic slip that occurs on the slip plane. Something like this happens. Now, slip planes there's just not one slip plane, there are complementary slip planes, and many slip planes are here. So what happens is ultimately you get this. So you have an extension of crack by an amount delta A. This was the original point of the crack, and here it has extended by delta A as a result of all these slips. Now, because this area is very highly stressed, so plastic deformation takes place here, and a blunting of the crack tip occurs. There's the same point here. There was stress concentration here, as was here, very high stresses. So, but here, because the blunting occurs, there's no stress concentration anymore, because stress concentration is where you have a sharp corner. So after blunting, this is the situation. There's no extension anymore. Now, this would have this all is loading. If it was static loading, here the story would have ended. It would have extended a bit, but that's about it. No more extension. That's all. But what happens in dynamic loading? Either magnitude will change or the direction changes. In either case, it doesn't make much difference. If the direction changes, obviously then you are talking about compression. Even if you are talking about unloading, not changing of load, but just removal of the load, then this thing again becomes, and in case of compression, that is more the case. This thing again becomes like this, again sharp. Hence, again there is stress concentration. So what happens is, as a result of one cycle of loading and unloading, the crack has extended by some small amount. And what's more, if it was just loading, static loading, then it doesn't make a difference. This is maybe an atomic distance, one bond distance. But the dangerous thing here is that as a result of unloading, you again have a sharp corner here. So the next time you again apply the loading, because it's fluctuating load, it's going to again come in a cycle. The next time you apply a tensile load, it is pretty much the same situation as it was here. So it will again go through the same process. So in every step, it keeps on increasing. So it's a slow process, but it happens. Now, the next question, and this is very practical for us. Can fatigue be avoided? We tend to avoid those things that are unpleasant, and in many cases we find out that there's no avoiding them. They are just part of life, and so is fatigue. So the answer is no. It can only be managed. You have to make sure that you design based on fatigue. You don't get any surprises because of fatigue. That's all you can do. And the next question is again very relevant to this question and to all the engineers, and that will be, how does a given material respond to fatigue? You are interested in designing a component. You have some material in mind. Now you want to find out how does that material responds to fatigue. Now, unfortunately, there's no analytical method here. You cannot start from some basic assumptions and then you can reach some conclusions, because fatigue is completely an empirical thing, empirical phenomenon. Empirical means experience based experiment. You have to do a test, just like we did tensile test to know how a material responds to static loading. Here we also need a test, and that test is called very famous rotating beam test credited to R more. Now, what that test does is simply subject a specimen, and this specimen is specified like all tests. AST. It's important to test anything according to some standards, because if everybody starts testing on their own, then there'll be no way of comparing the results, and it will be just like a case where different people, like in a sitcom, different people are talking about the same thing, but they have different things in mind. So this specimen, roughly speaking, it is of this shape, and you can refer to your textbook for the dimensions and the details. Here we are just going to consider the principles. Now, this material is designed to fail in this region. How it's made to fail? First of all, the loading. Obviously, if we talk about details, there'll be some bearings and there'll be some belts, and loads will be hung here. It will be connected through a coupling to a motor. There'll be some sort of a counter that records the number of cycles, and symbolically, I beg your pardon, this is where the belts carry the load, and some sort of bearing is here which supports this, and obviously this is circulating. Now, I think it's very easy to draw the shearing force diagram and the bending moment diagram for this. This is shear force diagram, and the next one is bending moment diagram. The important thing is, in the region of interest, this constant bending moment, because essentially this is a 4-point bending test. 4-point bending, you have heard about this. Only this is not only a beam, but it's also rotating. So the stress, what sort of stress would you expect here? We have a bending moment, let's call it M max here, and what kind of stress this element will be undergoing? It's very simple, minus M max by this is the stress here. Only if you consider that this is also rotating, so at one instant it is tensile, but after half the revolution it will become compressive, because this point now comes here and the bottom point comes at the top, and again after half the revolution it again comes to the same place. So what we are talking about here is something like this sort of a situation. And obviously it continues. Continues like this. And this is the sigma max. We're talking about sigma min will be similarly on the other side, only it is the same magnitude, just opposite sign. This is what it is. So what happens is, this, according to ASTM standard, this is polished carefully so that there are no scratches. As a result of loading, obviously this bending moment, because of that fractional stresses are here and they keep on changing, so it's fluctuating load causing fatigue. Some cracks will initiate and then they will grow, and they'll keep on growing until a time when critical crack length is achieved, and then it will just break in two. At that point, the number of cycles, revolutions, are recorded for that stress level. Obviously, it's very obvious that for higher stress levels, you'll have more number of revolutions, and for low stress levels, you'll have high number of revolutions, because obviously, the if you subject this to a very low stress, then obviously the critical crack length will be very high. So the fluctuations will keep on increasing the crack length, but it will take a longer time, and vice versa. So these should be inversely proportional. We don't know the exact nature of their proportionality, but if this is high, then this must be low. If this is low, then this must be high. We don't know the details, so we'll take that later on. If we subject any material to this sort of loading, and what happens is, at the time the material breaks, some sort of signal is sent to the motor to stop, and the number of revolutions at that time is recorded. So now, what do we get as a result of one such test? Actually, we get two different types of results. If we plot the results as we get them, they don't tell us a lot. But if we, this is the log of stress levels, and this is log of the number of revolutions. This tells us a very neat story. For one kind of material, and that is ferrous metals and steels, for example, because they are so predominantly used. So even if this is only for steels, it is very important for us. And for non-ferrous metals, for example, aluminum, alloys, etc., we get a somewhat different kind of a graph. Remember that these are log scales. So this is 10 raised to power 0, 10 raised to power 1, 10 raised to power 2, 10 raised to power 3, 4, 5, 6, 7, 8, and so on. Similarly, 0, 10 raised to power 1, 10 raised to power 2, 10 raised to power 3, 10 raised to power 4, 10 raised to power 5, 10 raised to power 6, 10 raised to power 7, 10 raised to power 8, and so on. We get this sort of a figure. I'll discuss this later on because there is a lot of detail about this. There's a knee here, and after this it straightens. What it tells us is that as you keep on increasing the number of as you keep on increasing the stress levels, the number of revolutions before breakage occurs becomes lower and lower, which makes sense. Obviously this detail we wouldn't have known, but we know that as this increases, this should decrease. But a strange thing happens. After around 10 raised to power 6, after about a certain stress level, at this stress level, the material can seemingly work indefinitely. It will never break. There's a lot of detail here, but we'll discuss that later. And this is called the endurance limit of the material. There is a lot of discussion about this. We'll do it when it's necessary. On the other hand, for other non-ferrous metals and alloys, we don't get this kind of an E. There's no endurance limit. So we may have the same some value for something like this. Something happens at 10 raised to power 3, and then something else happens after that. But this kind of, there's no knee here, so it keeps on decreasing, maybe at a very low slope, but it there's no straight line here. So here, this region till 10 raised to power 3, 1000 revolutions, this is called low cycle fatigue. And after this, anything after this is called high cycle fatigue, HCF. This is LCF. Similarly here, this is low cycle fatigue, and anything after this is high cycle fatigue. Now, for ferrous metals, steels only, this region is called finite life region. Finite life. And this one is infinite life. Basically, what we are talking about here is that you have if you keep the loads, fluctuating loads lower than this, then it will work for infinite life. But if the loads are between this and this region, then you have a case of finite life. Now, this one is finite life, this is infinite life. In case of non-ferrous metals, there is no concept of finite or infinite. There's anything, all this is finite life. So if you are going to design an engine part, it makes sense to make it of steel, and that is the way we do it, because for a car engine, this sort of loading occurs very quickly. So we are using it in this region somewhere. So it makes sense to design it using ferrous metal, as we do normally. Now, this is the basically breakdown of the two regions, high cycle fatigue and low cycle fatigue. Now, what about how is fatigue life predicted? This is our next question. Now we know that there are different regions, and how is fatigue life predicted? There are three methods basically. One is stress life approach. The other one is strain life approach. And the third is linear elastic fracture mechanics. Linear elastic fracture mechanics method. These are the three methods that are used to design different products using these three approaches, and for different applications. Now, first of all, let's talk about the stress life approach. Now, this is probably the most expensive, the most frequently used approach, and this is for mass produced cheap cheaper parts in which inspection etc. is not feasible. Most of your household goods, your automobiles, this is a very frequently used approach. Now, this approach is also used for, actually, this is, we are talking about, this is used in the high cycle fatigue region. When it comes to strain life approach, this deals with low cycle fatigue. Those things that are that highly stressed and the life cycle is around 1000 cycle or something. Now this may be important but not as important as this one. So here we'll mostly skip it. For this course we are going to skip it. What about the linear elastic fracture mechanics approach? This approach is used for large one-off products. Generally speaking, there may be exceptions, such as aeroplanes, where inspections are a routine. We have the luxury of inspecting our aircraft, their wings, their fuselages, and if there is a crack there, we we anticipate that there will be cracks there, and we design them on that basis. And when a crack is noticed, then it is managed after that. For example, there's a certain procedure of inspection, and then either you replace the part or you repair the part. So that kind of luxury is not there for your washing machine, for example. So we don't have this kind of an approach for that. So this one also is there will be we will discuss this one also, LEFM, but not in that much detail as the first one. So this will be discussed in the most detail. This is most probably the most important as far as the beginners are concerned. We'll also discuss this, but we'll skip this one. Interested parties can look this up in literature which is widely available. Now let's talk about some other questions. What are fatigue cracks like? What sort of cracks are there? Now we had discussed, we have just discussed that this is what happens in one cycle. In one cycle, you have an extension by delta A. In the next cycle, there is again delta A, and so on. So one would expect that this sort of gradual, in every cycle, this small amount of extension, this should leave some mark on the material. For example, you are presented with a failed specimen which broke by fatigue. How do you know it was fatigue? So the signs are pretty telltale. You can look at a crack and it's probably very obvious that it's a fatigue crack. For one, fatigue cracks usually, again, there are start at surfaces. There are exceptions. There could be cracks that start from inside the material, especially when there are interfaces and and voids or something like that. But usually they start at the surface. And where do they start? Because of tool marks, discontinuities, any sort of discontinuity, and misuse, yes, damage. Most of the damage occurs at the surface. Design features. For example, there's a key. You are going to use a key, then there will be a keyway, and the keyway will have a certain corner. So these design features are unavoidable for design. So wear, it could wear. There are cracks that start from the effects of wear. There could be stamps. You apply a stamp, and it could start a crack. So mostly they start at the surfaces, although there are exceptions. And because, for example, let's take cross section of a shaft, which was subjected to some sort of bending also. Now there's a keyway here. We just talked about the keyway. So this crack can start from here, and when it starts from something like this, it keeps on increasing, and these lines, these are the lines that mark each growth, delta A each, and these are called striations. You can, they are not visible to the naked eye, but you can look at some micrograph and they'll be visible, and it keeps on increasing, and at a certain time critical crack length will be achieved, and the remaining part there will be no striations here. It will just break in one go. So it will be very clean here. It's clean also here, but there will be striations here. So this kind of a crack is it will start from surface, some sort of surface tool mark or discontinuity or something like that, and then it'll keep on increasing. There will be striations, and the remaining part it will just break in one go. There will be no striations here. So it is very easy to identify a fatigue crack. Now another thing about the fatigue crack is that some sort of bending is usually there. Again, there are exceptions. You could have cracks because of torque and everything, and axial loading and whatnot. But bending, the best way to break anything, in fact, is bending. And this is also true for fatigue. Bending actually introduces a big lever, a big moment arm. So it's very easy for anything to be broken by bending, and fatigue is no exception. Now, if we revise whatever we did today, then I think this should be enough for now, and we'll take up this thread where we leave it today. So we'll just go through the summary of what we did. Fatigue is a difficult and lengthy thing to learn, so buckle up. It's not going to end very soon, but we have made a good start today. So if we revise the salient points, what we have discussed. What is fatigue? Where does it fit in? Fatigue. The process is something like this. Cracks are initiated or micro cracks are already present. All materials will have some sorts of micro cracks or defects. So cracks are already there, but even if they are not there, we have just discussed that even if something is perfect, no cracks, you have polished it, still at some discontinuity, at some design feature, at some point during use, if not during fabrication or assembly, they'll be initiated at the points where there are stress concentrations, and then they'll grow. Or in other cases they are already there from the start, but they are obviously subcritical crack lengths. Now cracks grow under variable loading. This is the second point. The third step is cracks become unstable. Critical crack length is achieved and fail in a brittle manner. Now, so the fatigue comes in. This is fatigue. This you have already done, and this is a fact of life you should know. Now, some other points that we should. Fatigue is an empirical phenomenon. This is also we have seen. Anything that we know about fatigue is because we ran a lot of tests, we had a lot of accidents, we learned from those accidents, and now we are hoping that we don't repeat those mistakes. That is fatigue. Now fatigue is a statistical phenomena too. When I said statistical, it depends on the flaws in a component. Depends on flaws in a component. Now, what do we know about flaws? The cracks. They are statistically distributed and oriented in a material or a component. For example, if you are pulling like this, and obviously it's a fluctuating kind of thing, this kind of crack is different from this kind of crack, and all sorts of cracks are there statistically located. Now in some material more than in others, but so it all depends on the statistics. More of this statistical distribution in our next class. Thank you very much.